Right. We saw this OSPF adjacency states. Let's go more deeper to understand what exactly happens. As we all know, init state here means one of the router has already said hello, other router has heard. But it's not two-way. But when the other router also says hello along with the neighbor address of the first one, and when the first one receives that hello from the second one, then it forms two-way. So in this stage, A knows exactly the name of the next B, means the router ID of B, and B also knows the router ID of A. Router ID only is used by OSPF to identify the OSPF running device. OSPF will not use this sending address as the router ID. OSPF will see what is inside as an ID. In this example, the sender address is also a router ID, but not always the router ID and the source address be same. It's not always same. Let's take a scenario like this. We have a loopback interface, and the IP address of this loopback interface is 1.1.1.1, and this is 2.2.2.2. So B send or A send the address with the router ID 1.1.1.1. But the source address of the packet is this. Inside the packet, inside the OSPF header, this is what will be shown as the ID of a sender. In short, ID of a sender and the source address from where the packet is coming need not to be same. When we don't have loopback interface and there is only one address on the router, that becomes the router ID also. But when you have a loopback interface, OSPF will prefer the loopback interface address as the ID. So with this ID inside the OSPF header, with this as the source IP and this as the destination IP, the packet goes. Now B router receives the packet, learns neighbor address as 1.1.1.1 via E1. It learns. And now when B sends the hello packet, in the hello packet there will be neighbor list. In that neighbor list, it puts 1.1.1.1 and the router ID as 2.2.2.2. Send the packet to this address. This is the address from where the packet was coming. So it is sending to this address, not the multicast address. This time it is unicast address. Now A receives the packet. When it receives the packet, it can find its own address as the neighbor of B. And also it learns the neighbor in the neighbor table via E0. This forms two-way between these two routers. As we learned earlier, between these two routers, there is an election process. What election? How long this election posting continue? This posting, yeah, until it chooses who is master and who is slave. Yes, You see, in a serial environment, in the serial, in the serial port, which is point to point, yeah, correct, correct. How it is to dot, sorry, it is wrong. It is one dot one dot one dot one. According to, okay, A is neighbor list. You are right. Sorry. Hmm. A is neighbor list should be two dot two dot two dot two. You are right. Hmm. That's right. Very correct. Fine. So when router A finds its own address as the neighbors list, it accepts the sender's router ID as the neighbor, and it includes in the neighbor table. All right, let's go to the next page. So here what we are seeing is, assume this is a serial port, not an Ethernet port. Assume it as a serial port. In serial port, all the conversations except the hello packet, all the conversations are multicast. All the conversations are multicast. So let's finish the serial port conversation. Then we will get into broadcast, multi or broadcast type. This is serial port, which means point to point. In point to point, except hollow packet, all other sorry, in point to point, all conversations are multicasting. Multicast. They use multicast. In broadcast only, it differs. So we'll talk about broadcast later. Let us finish this properly. So this is point to point, which means even in the previous page, this is not an unicast. This is a multicast. If it is serial, if it is serial, it's multicast. Okay. Now these two routers undergo election. Yes, in point to point also there is election. In broadcast also there is election. When I say broadcast, it means Ethernet segment. In point to point also we have election, but the role of these routers will not be same, will not be maintained once they form full adjacency. I repeat it. Till they form full adjacency, they will have a role to play. The router with the bigger router ID, according to our conversation, according to our discussion example, the router ID of this router is 111 because it is taken from the loopback interface. It prefers the loopback interface address to be the router ID. So compared to these two, R2 becomes master. It's not DR. If it is point to point, there is no DR BDR. This becomes master. And this becomes slave. This is a temporary role. Later we will be seeing broadcast. There will be something called designated router DR. That role is permanent. But this role, master slave, is just for time being. Temporary role. Once the neighbor is established, there won't be any master, no slave. Both are same. But during this mid time, in the extract state, the router with the bigger router ID will say, we are not slave. We are masters. We are master. Router 1 will agree saying we are slave. Because router 1 knows that the other router has got bigger router ID. So now the master will initiate the exchange of DBD, and then acknowledgement will be sent, and then DBD from R1 will be sent, and then acknowledgement will be sent. That is what we call as exchange state. Now the loading state is during the exchange, the informations were not shared in depth, in detail. The informations were summarized. DBD is a summary of LSDB. So between these two routers, there may be some queries. Those queries are sent as LSR, link state request. Queries are sent as LSR. And then the response comes from, okay, for this query, once the other router receives the query, LSR, it will send an acknowledgement. It will say, I got your query, I got your LSR. After that, the query is responded now as LSU, link state update. Once the LSU is received, acknowledgement is sent. And when there is no more query to be raised, they both reach state called full state. So both the router declares that we have reached full state of adjacency, meaning I have understood all the info that you have sent me and you are my neighbor. We are going to see this one first in the demo, and then we'll go to a broadcast environment. There also we will have another demo. But let us first of all finish this point-to-point. Now our focus is only between router 2 and 1 and 2. Okay. So our focus is only here. We have OSPF already running. I'm going to go under interface serial 4/0 shutdown on both sides. I shut down. Also, we can see here once I shut down, there is no more neighbor. Neighbor has fallen down from full state. So both sides we can see neighbor is stopped. The reason why I shut down is I would like to enable debug IP OSPF event command, which will show every single conversation, and then adjacency. Without putting debug command, we cannot see the conversations. They're all done behind the screen. But if you wish to see every single negotiation that they do between, then you need to put debug. It's not only for OSPF, for EIGRP, for every protocol we have debugs. Even when you do ping, for ICMP you have debugs. All right, now I'll also enable this to debug on router 2. Correct. Correct. That will help to troubleshoot, not only to troubleshoot, also to learn the things happening behind. So here our purpose, our aim is to see those 7 stages, to see what is happening, not to troubleshoot. We don't have any trouble here. We are just doing this to understand ADHA. Okay. Now I'll go say no shutdown so that the OSPF adjacency will happen. No shut here. Same way. Okay, I hit enter here as well as here. First, the line protocol will come up and then OSPF. Okay, all right, done. I can already see loading to full. So let us stop this debug. You all will stop the debugs. Here also you all. And this debug command, show command, you all command, all these commands go on the enable mode or the privilege mode, which is one step before the global configuration mode. Right. Go to the top. You see the interface has come up and the interface change state up, and it's a OSPF point-to-point link. I can see two-way state. Some operating system can even show you init state. No, this didn't show init state, but you can see here both the routers have learned each other's name. After that, they want to send DBD, but they cannot send. For that, they come to an agreement. This guy says, we are slave. The reason is router 1's router ID is 1.1.1.1. And router 2's router ID is 2.2.2.2. So router 1 will say, I'm showing this on router 1, it will say, we are slave. Whereas router 2 will say, in the extract state, it will say, we are not slave. We are master. Because I am master, I'm sending the DBD first. So the master sends the DBD, and then R1 will also send the DBD. Okay, it receives and then it sends the DBD. And then the extract states get over now. A loading is also now over. Sorry, exchange is also over. Extract is master slave. Exchange is low. Exchange is just sharing DBD, and then comes the LSR, link state request, and then link state updates sent for the request sent by the other guy. Here also you can see LSR, LSU, sent and received. That completes the loading state. Sorry, yeah, exchange gets over. This is loading actually. know why exchanges come here. This is actually after exchange. LSR and LSU is after exchange. Okay, still the exchange is going on. So this is what loading state. Once there is no more to load, it says, and we are synchronized with so and so, we have reached from loading to full state. Loading to full done. All right, this is between point-to-point neighbors. Point-to-point neighbors. Let me shut down one more time. And I would like to use Wireshark to show you they use multicast for all conversation. Okay, OSPF has gone down. I'm going to start the Wireshark these two. Why nothing is coming? Because the port is down. Let's go bring it up. No shut and no shut. I remember I showed you all types of packets, same like this yesterday, and all were using only multicast. You can see here LSA link state acknowledgement using multicast, and then link state update is using multicast, and then link state request is also using multicast, and then DBD is also using multicast, and then the hello packets also using multicast. Now, okay, where it is, what did you say? Where? Okay, this one is like, layer one kind of keep alive message. It's just a ping message between these two devices. Even when there is no IP error, this will happen if the interface is up. That is to say that we both are up. We can communicate each other. That's kind of signaling. Like when we call someone, we say hello. We did not call to say hello. We called to say, I'm fine. How you are doing? That's why we called. But still, we don't start conversation without saying hello. So this is a kind of hello. Cisco, see, keep alive. That's called keep alive. Cisco's routers, they send the hellos. Okay, now that's not OSPF related. If you see all OSPF related packets, okay, filter here, show me only OSPF packets. Any packet you take, it is having the destination address as multicast address. In point to point, it is always multicast. Okay. Now, even though it is sending the source address as the exit interface address, if you open the packet and go to the OSPF, you will see they use loopback address as the ID. You see, the routers, the OSPF router source is 1111. Actually, the packet source is 10.12.0. Which one I clicked? Let's click it. Okay, this one. The packet source is 10.12.01, but the OSPF is not considering that as the as the sender of the packet. It says the sender is 1111. OSPF deals using a router ID, not the source address of the packet. Okay. Now, I'd like to ask you a question. Try answering. What type number? OSPF type number. See, for example, hello message type number is 1. What is the type number for LSE? U. LSA is there, LSU, is update. LSU means what? Link state update. You remember LSA, LSA, LSR, LSU. LSR and LSU is sent during the loading state. LSR and LSU are sent. It's a request and response, isn't it? LSR is request. LSU is response. Now, what is the message type? OSPF message type number. LSR. Okay, LSU. LSU. Correct. See, I'm going to type 4 here. I cut 1, I put 4 here. You will see all LSUs. So this is 4 LSUs sent between these two routes. And now if I type here 2, what will I get? If I hit enter now, correct database description. Correct. Okay. So now our focus is now turning towards um, broadcast. See, this one, what you saw now is point to point. In point to point, we see master and slave. See, show IP OSPF neighbor. Is there any slave now? No. Once the adjacency is full, it won't maintain that state, slave master. Only during that exchange state, they need it. Only during the exchange state, they need it. After that, no more master, no more slave. But that is not the story with the broadcast. This one is point to point. I will show you in 2 places. This is point to point. Show IP OSPF interface brief. You can see the serial 40 is shown as point to point. This is point to point. Not only that, if you type show IP OSPF interface serial 4/0, you can see network type as point to point. What is the network type? It's point to point. After, we will be focusing on this area. For this F00, if I check, it will show broadcast. Let us try checking it now. Show IP OSPF interface. You can see here broadcast. In broadcast, there will be DR BDR election in this state called X start state. X start state comes after what? Two-way. Correct? X start state comes after two-way state. Yeah. During the X start state, in point to point, what happened? Master slave happened. Master slave role was decided. In a broadcast network type environment, what will happen is DR-BDR election will happen. What is DR-BDR? Why do we need DR-BDR? Story comes later. Don't think about that now. But what I'm trying to say is, in a broadcast network type environment, there will be a role called DR for one of the router, BDR for another router, and for all rest of the routers, there will be a name given called DR others. DR others, that's the name. We'll talk about that in detail later. But now we will only focus on this adjacency state in a broadcast network type. In a broadcast network type, we will see that 7 states of adjacency. So I'm going to shut down router 1. Router 1 is no more needed for us. And Wireshark also I'll close because this is between router 1 and 2. Okay. Now I would like to start the other 3 routers. And our focus now is inside this rectangle. Okay, recording. Now we got these 4 routers running, but the interfaces are shut down. I'll capture this port. Can I capture on the switch? Oh, the switch. Not possible. Okay. Can capture anywhere and any on any interface. I'm going to do a capture here. Okay. There's no packets, nothing moving because all the ports are down. Let's bring it up. No shit. Okay. You can see ARP request. ARP is asking who is that 10, 25, 34, 3. Alright, so OSPF hello packets are going from every router. You can see it's coming from 5, 4, 2, 3. Still the election is going on. They may be in now a start state deciding who is DR, BDR. So, this is guy is DR. DVD I can see. Okay, all have now shared the update to the DR. Let's go and check. Go to router 2 and see now. Show IP OSPF neighbor. You can see router 5 has taken DR posting. Router 4 has taken BDR posting. With router 3, it is only two-way and DR other. Understand? What is two-way? I know you, you know me. That's it. No synchronization of database. So now it's time to understand why DR, what is DR, why BDR, all those stories. Let's minimize this. Okay. So what is here we have is 55 as the router loopback address, and then here it is 4.4.4.4. So the hello packets are sent using this router IDs. They all compare the router ID during the start state, and then router 5 will say, I am backup designated router. It will say, I am backup designated router because I think I have the biggest router ID. And when there is, yeah, the biggest. No, wait. I'm just explaining the actual procedure, what is happening behind. So first router 5 will say, I think I'm having the biggest router ID, so I will take the role of BDR. And then when there is no objection from any other router, it promotes itself to DR. That is the procedure. Because in OSPF, no routers can become directly DR. OSPF is not designed like that. First, it will take the role of BDR, and then when there is no objection, it will promote to DR. If this is promoted to DR, then immediately router 4 will say, I will take the role of BDR and wait to become a DR. Router 4 is saying, I am taking BDR posting because I'm the next biggest one, and then I will wait to become a DR. Immediately router 5 will say, hello, I'm here, I'm DR. Okay, I know that. I know that router 5, I know you are a DR, but I will wait for you to go. Until then, I will continue as BDR. Is there any problem? Router 5 will say, it's okay, man. Be a BDR. And then router 4 says, yes, I'm a BDR. And this is now known to router 2 and router 3. If you go to router 2 and check, it says router 5 has got a DR posting with full adjacency, meaning everyone will go and give every info to DR. Even if you go check router 3, show IP OSPF neighbor, router 3 also says to these two guys, we have full adjacency. But router 3 says with router 2, I'm not having full adjacency. I'm just having 2. Meaning I am not going to give him anything. I'm not going to share with him any info. Why? I am not authorized to do that. I am a DR other. DR other cannot talk to another DR other. DR other should report only to DR and BDR. That is why it is reporting everything to DR and BDR and from full state. That it's the same case with router 2, full state. But between 3 and 2, they don't share anything. They don't go to extract state. They stay in two-way state always. Then how? Then how? Router 2 knows all the info of router 3. It knows through DR. That's the role of DR. Now let's see in more in depth. This is DR. Why do we need DR, BDR, DR other? Why do we need this role? Before coming to that, yeah, before coming to that, how this R5 became a DR, it is because of the bigger router ID. What if I want router 2 to become a DR? Assume we have a hub and spoke topology. R2 is a hub, R3, 4, and 5 are spokes. And I wish to have router 2 as a DR. Is there any? Okay. This is hub and spoke. You see, in a cycle, you have a wheel. In bicycles, you have wheels. Netherlands is full of cycles only. So you have wheel. And in the wheel, there are spokes. And that spokes is connected to the rim. And in the middle, there is a hub. This hub is the center of that rim, that wheel. And the strings connects the rim and the hub. That makes the rim to spin when pedaling, during pedaling. It's the same here you see. This is what? You see, this is router 2. And this is router 4, router 5, router 3. This type of design is what called as hub and spoke design. R3, R5, and R4, they are connected via router 2. That is hub and spoke. But this is not literally hub and spoke because you got a switch here. Instead of switch, if you bring this router 2 here, then it is real hub and spoke. This looks like a hub and spoke. Now, why this is not hub and spoke and this is hub and spoke? This is not hub and spoke because R3 can talk like this. R5 can also talk like this. Whereas in hub and spoke, R3 cannot talk directly to 5. It goes to 2 and 2 helps to redirect the traffic to 5. Yep. So now what we are talking is, assume I don't want R5 to be a DR, but by default R5 becomes a DR, R4 becomes a BDR. I want only R2 to become a DR, and I don't care who is BDR, but my expectation is for the 2 to become a DR. Is there any way? Yes, there is a way. The default priority is 1. The default priority is 1. The default priority is 1. Let's focus on our topology. Everywhere the priority is 1. By setting priority 100, I can make this as a DR. See, that is what I have also set here. The default priority is what? 1 only. But in the previous class, sometime before, I have set 50 for router 4 and 100 for router 5. So, in short, what I want to say is, during the election time, see now the election, everything got over. During the election time, first they compare the priority. Only when there is a tie-in priority between these routers, they compare the router ID. Understand? If priority is a tie break, it won't go to router ID. Let me show you that. You see, I have set priority 100 on router 5. I can see that in router 3. Let me go and show it in router 5 itself. Show run interface F00. You can see I have set the priority 100. Likewise on router 4, I have set priority as 1. Show run interface F00. See, I have set 50. Whereas on 3, I did not set anything. Show running interface F00. See, I did not set anything. When you don't set anything, what is the default? 1. How will you know? There are 2 ways. You go to router 2, you can see router 3's priority as 1. Or in router 3 itself, if you want to see, you can type show IP OSPF interface F00. The same command which I was typing sometime early, where I showed you network type, you also see what? Priority. The default priority is 1. Now what we will do, we will make router 2 as a DR. We are going to set priority highest. The highest priority is 255. I'm going to set priority here, highest, and this is already 100, and this is 50. Now this is the highest, and this I'm going to give 200. So what do you expect when the re-election happens? R2 will become what? When the re-election happens, R2 becomes what? Correct. Why? Correct. Which one will be the BDR? Right. Let's check that one. For this, first of all, let's go set the priority. Right now, show run interface F00. I did not set any priority. Go inside and set IP OSPF priority. This is the command, and this is the maximum. You see in the bracket 0 to 255. And now it won't take any effect because the election is already over. I'm just setting now. We need to conduct a re-election. I'll conduct it. First, let's set the priority. On 3, we are going to say IP OSPF priority 200. Okay. Now, how do you conduct a re-election for this? One thing is you can shut down the ports. 1 minute, please. I'm just saving it. Okay. I can shut down all the routers. Okay. I've shut down all the OSPF ports facing towards this broadcast network. The LAN facing the switch. Now let us start. I'm not hitting enter, I'll just keep it ready. Okay. So now the re-election is going to happen during the start state, and once they reach full state, we'll go and verify. We should see router 2 as a DR with full adjacency. Router 3 as a BDR with full adjacency, whereas 4 and 5 will be DR other two-way state. Still election is going on. Okay. Let's verify. Now I'll go to router 5 and check. Show IP OSPF neighbor is one command which we used to check DR BDR. You can see here, this is DR. 222, full adjacency. This is BDR because this is in two-way state. You can also see this in another command, show IP OSPF interface F00. Here it shows that the DR is 2222, BDR is 3333. Is it clear? Okay. So what do you understand from here? The DR posting is only by promotion. I told you there is no direct DR election. First it becomes BDR, then it becomes DR. And second thing what we learn here is, once the election is over, whatever the priority you may change, you may give a better priority, higher priority, the role change won't happen. Because the roles, the DR, BDR roles are non-preemptive. 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 Meaning, once election has happened, It is done. After election, if someone comes and says, I got the highest vote, give me the post. Sorry, wait for next election. You wait for next election. Okay, now let's say this is the DR. Correct. Yeah, whatever big you bring, it cannot become a DR or BDR because already a DR and BDR is there. Okay, let's change the scenario here. Let's take this as 1 and this as 1 priority, and now this is DR and this is BDR. Now what happened after election? After election, you are changing this to 255. We changed it actually. Was there any change in the role? No, it won't happen. It won't happen. The role change won't happen. The DR BDR roles are non-preemptive. So when will be the effect of this priority change I made? I have changed priority to 255 on router 2. When will be the effect? When can I see the effect of this change? You will see if this goes down. If this goes down, this guy is waiting in the queue to become a DR. So this guy will say, hey, I am DR now. Now the election is between these two guys. This guy says, see, I have the bigger priority. You may have a bigger router ID, but what comes first is priority. So router 2 says, I will be BDR. Even though it has got 255, this still it cannot become a DR. It has to wait. Now what happens? This poor guy comes back. He comes back. What will happen to this guy? He have to become a DR other only. Why? Because DR BDR is already there. Election is over. This is what called as non-preemptive. The roles are non-preemptive. Now, one more thing we need to understand in this topic is why we need DR BDR, DR other. Why we need these elections. What if I don't have this DR BDR, DR other election? If you don't have, what will happen is loop will occur. Loop will occur. How? Everyone will start exchanging to everyone. Let's say I exchange to you, but I also exchange to him and her. I have exchanged to you, him, and her. But what you thought is, whatever I give, whatever I get, I have to give to everyone. So what you do, you also send to him a copy of what I sent also to her. So what that happens, that becomes duplicate. Him also what him do, him will send whatever he received from me to you and her. And her also whatever she received from me sends to him and you. So this becomes like, duplication of update, and that will cause loop. To avoid this, we will only give the updates to DR, and DR will give to others. When there is an update is sent only to DR and BDR, but BDR will not send to others, only DR will send to others. By doing so, loop is prevented. By doing so, loop is prevented. Let's say like this: father, mother, elder brother, younger brother, elder brother, younger sister, elder sister. Now, father and mother are like DR and BDR. Yeah. So instead of we sending everyone sending everything to everyone, it will create loop duplicate of updates. When the brother or sister wants to send some update to update to some the family, he or she sends to the father and mother, and now father sends to elder sister, elder brother, younger sister the info. The info was sent by younger brother to father and mother, but father only forwards that message to rest of the members of the family. Mother has already received, but mother will not be sharing to children. It's only father. When father is away, mother also has got a copy. So if anyone wants any update, they will send a LSR query. Now mother is the DR because father has gone far away. So mother can give the update. And now the eldest of all becomes the BDR. Things like that. Okay. So that prevents loop. That prevents loop. So in a point-to-point environment, there is no DRBDR needed. அச்சாலும் பிடிச்சாலும் இந்த ஆளுக்கு இந்த ஆள் தான் இவங்ககிட்ட தான் கொடுத்தாகணும், வேற யாரும் கொடுக்கறதுக்கோ வாங்குறதுக்கோ இல்லை. இவங்க ரெண்டு பேர் தான். இதுலன்னா நான் லீடரு நீ லீடர் இருக்கிறதே ரெண்டு பேர். நான் பெரியவன் நீ பெரியவன். ரெண்டு பேருக்குள்ளே ஒற்றுமை இல்லைன்னா உலகத்தை இருந்தா சமாதானத்தை யாரு என்ன நெல்லி நட்ட போற. So whatever R1 has got, it will just send to a multicast. It will go only to this guy. No one will receive it because there is no one else in the serial link. But that is not the case in the Ethernet. If this guy sends, everyone gets it. If the same thing this guy sends, it becomes duplicate for all of them. To avoid that only we need DRBDR. All right. So when there is no DRBDR, whatever the priority you may set, it's of no use. You see, in point-to-point network, the priority by default it is 0. In point-to-point network, the priority by default is 0. Will you be able to change the priority? Yes, you can change, but will it be effective? No, it won't be effective. It won't be effective. It won't make any difference. Even for electing master slave, no, during the extart state, only the router ID is involved in point-to-point. You understand? Point-to-point routers will never focus on priority. Whereas multi-point means that broadcast environment focuses on priority first. When there is tie in the priority, then it focuses on router ID. Now, in this, the only multicast address involved is 224.0.0.5. Whereas in this, two multicast addresses are there, 224.0.0.5 and 224.0.0.6. We'll discuss on this thing in our next class in detail. We will see why we need this two multicast address, how it is used, who will use, all the stuff. Any question from today's class? Okay, tomorrow then we'll see. Hmm. 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 You got the answer? No problem. We'll discuss again. Huh? Okay. See you then tomorrow. Take care. Have a wonderful